In this section 2.5, we are using our linear function in a real life problem. Okay, so we use linear model. Okay, and in this linear model, using a given data, we find the linear function. We were able to predict using a linear function. Okay, so in linear model, we always try to find the linear function. Okay, now here we can also use curve fitting to find our linear model. Okay, and for that we have guidelines for curve fitting here. The very first step is that we have to identify the appropriate input variable and output variable. Okay, we will be given a data set, and for that, from that given set, we need to know, we need to identify our input variable and output variable. Output variable, these are dependent. Okay, output variable, it always depend on some other factor. Input variable is independent variable. Okay, and next we set up a coordinate system and plot the given points. Okay, that is our second step. Once we have our input output, we can plot the given points, okay, on our coordinate system. Now in this class we will use our hand to graph. Okay, not the graphing utility. You can still use a graphing calculator to graph. Okay, but we'll be using our hand to graph this given data set. Now once we plot those points, we observe the trend in the scatter plot. Okay, we have a data set, we plot those data set, that is a scatter plot, and in the scatter plot we observe the trend. We will see how the points are. Okay, whether the points are in a straight line or the points are in a parabola, or what is the shape of those points. Okay, we'll try to find the shape from those points. And once we have that, we will once our scatter plot represent, we have, once our points they are in a straight line, we will use a linear function. Okay, we will find a straight line to represent those scatter plot. Okay, so at first we identify input, we identify output. Second step, we plot those given points. Okay, third step, we observe those scatter plot. Okay, we will see how what kind of shape does the scatter plot give us. And the next thing in this section, we will be focusing on linear function. Okay, our trend line will be a linear function. Now here we have this data set. Okay, so here this table gives the body weight of a laboratory rats and the weights of their heart in grams. All data points are given to 5 significant digits. So we have a body weight, okay, of a rat and their weight of heart. So this is our body weight and this is our heart weight. At first we have to identify the input variable and output variable. Now out of body weight and heart weight, which one is independent or which one is dependent? So the when the body weight of a rat is 281.58 gram, the rat has a heart weight 1.0353. Okay, in the similar way, for the rat with a body weight 285.03, it has a heart weight 1.0534. So first step, we have to identify input variable and output variable. So which one will be our input variable and which one will be our output variable?
Body weight would be the input.
Body weight would be our input, and what would be the output? Heart weight, right? So heart weight, it depends on the body weight, right? So as the body weight is different, the heart weight is also different. So let's call our body weight as an input. Okay, so here this is our input, and let's represent our input by x. Okay, and our heart weight is our output. And what variable do we use for output? It's y in general, okay? But if you want to call any other variable, it's fine. But in general, we have x for input and y for output, okay? Now, let me rewrite all this measurement to a one significant digit, okay? And it will be easy for us. Let's rewrite all this data set in a one significant digit so that it will be easy for us to graph, okay? So here we have 281.58. When we round, this is 200, okay? Let me write to other side. So this will be 281.6, okay? We have 285.03, that is 285.0, right? 290.03, that is 290.0, 295.2, 300.6, 313.5, okay? In the similar way, let's rewrite our heart weight in a one significant digit. So this is 1 point, okay, it's gonna be 1.0. Okay, so this is 1.0. Now we have 1.05. This is 1.1. We have 1.07. 1.1. Okay, we're gonna get 1.1 a lot, right? So let's have at least 2 digit, okay? So this is 1.04, 1.05, 1.07, 1.10, 1.18, 1.27, okay? So we just rewrite, or you can use the original data set, okay? It's okay. So here we have our input, output. Now input and output together. So we have x, y together. It is a point, right? So let's write down our x and y together. So our x is 281.6. Y is 1.04. This is 1 point. Similarly, 285.0 and 1.05. This is our second point. Then we have 290.0, 1.07. This is our third point. 295.2, 1.10. So this is our next point. Then we have 300.6, 1.18. So this is our next point, and we have 313.5, 1.27. Okay, so these are the points. At first we identify input output. Next we rewrite input and output together in a order pair. That gives a point. Okay, now we plot this point in our Cartesian coordinate system. Okay, so let's go ahead and plot these points. So to plot, we need our y-axis, we need x-axis, okay? So this is our input, this is our y, which is output, this is our origin. Now, how do we start our scale? So our x values are 281.6, 285, 290, 295.2, 300.6, 313.5. So how do you want to start your scale? And when you are graphing, you always need a scale, okay? So so the smallest one is 281, right? So let's say this is our 280, then 285, 290, 300, 305, 310, 315. Okay, make sure you include the smallest. So smallest is 281.6 and the biggest number is 330. Okay, make sure you have those number on your x-axis. Now for the y-axis, we have 1.04, right, 1.05, 1.07, 1.1, 1.18, 1.27. Now how do you want to have a scale along the y-axis? Okay, so let's call this is our 0.1. okay, so 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. This is 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9. This is 2. Okay, now let's plot these points. So we have 281.6, 1.04. okay, 281.6. Let's find that on the x-axis first. Okay, so this is 280 and this is 285, right? So we have a 1, 2, 3, 4, 5. Okay, so 281.6. It's very close to 282, right? 281 is close to 282. And the next we have 1.04. So 1.04 is, what is, where is 1.0? So this is our 1, right? Okay, so our first point will be 282, 1.6. That is very close to 1 point. Okay, so this is our first point. Any question? And now next let's plot other points. So we have 285 and 1.05. So 285. So this is 285 and 1.05. Okay, okay, which one is bigger? 1.05 is bigger than 1.04, right? So we have a second point slightly above the first point. Okay, at 285. Is it at 200? No, this does not look at 285. So somewhere here. Okay, now the next 290 and 1.07. Okay, so 1.07, 290, so 1.07. So where will be that 1.07? Slightly above 1.05, right? Just it's okay if you do not have like a perfect, but since 1.07 is bigger than 1.05, so this will be slightly above this point at 290. Okay, so we have 290 here and slightly above first point, and that is our third point. Next we have 295 and 1.0. So now at 295 we have a point slightly above than this one, 1.1. okay, so 295, this is 90, this is 95, slightly above than the first point. Okay, next 300.6 and 1.18, which is 2. I think we messed up with the scale here, but it's fine. We have 300, so at 300 we draw a point which is slightly above than previous one. And the next we have 1 point at 313 So this is 313 and 1.27, which is 3. Okay, somewhere here, let's say. But yeah, so I think we need to redraw our scale here. Okay. So let me erase this scale here. Or so let's say our 2 is somewhere here. I think we should be fine. Okay, so basically here we plot these points. Okay, under exam I will make sure that you will have like a whole number. It will be easy for you to plot. Okay, now so this is our scatter plot. So we have data, so we identify our input, we identify our output. Input and output together gives a point. Okay, you plot all these points on your Cartesian coordinate system, and this is our scatter plot. Okay, we call this scatter plot. So this is our second step. Now we have to make an observation here. Now, what kind of graph does it look? Now we do not connect every points here. Okay, now using these points, we have to draw a straight line here. Okay. So in such a way that our every point is very close to that straight line. Now how can we draw a straight line here? So if we connect all these points, we do not get a straight line, right? We get something like a curve. Okay. Now our target is drawing a straight line in such a way that every points are very close to that straight line. Now how can we draw that straight line? Okay, let's draw a straight line and try to include as many as points on that straight line. Okay. Now, how many points can we include in our straight line? So we have 1, 2, 3, 4, 5, 6 points. So we draw a straight line in such a way that we include as many points as we can out of these 6 points. Okay, so here, let's see. So these 3 are exactly in a straight line, right? So we can include these 3 points, and this looks in a point. So let's draw a straight line. So here, let's see. See if we connect this way. Okay, so we have this straight line. Now, it doesn't mean you are not required to connect every dots. Okay, so we draw a straight line so that the distance of each point from the straight line is very minimum. Okay, we try to include as many as points on the straight line. Okay, so this is the best straight line or best fit that describe our data set. Okay, any question up to here? Now the next, our target is finding a linear function. Now we find the equation of this straight line. Now in order to find the equation of this straight line, what we need? How do we find the equation of a straight line? In order to find the equation of a straight line, at first we need to know what is the slope of a straight line, right? So let's find the slope of this straight line. Now how do we find a slope of a straight line? How do we find a slope of a straight line? We take any 2 points on that straight line and use our slope formula. Okay, so let's find the slope. So our slope formula m is y2 minus y1 divided by x2 minus x1. Now let's pick 2 points on that straight line. Okay, let's choose 2 points on the straight line. So let's pick this point. Okay, and the coordinate of this point is 300.6. So let's pick this point, 300.6, 1.18, 1.18. And let's pick one more point, okay, which is on the line. This one, let's try to pick this point. Okay, so this is our third point, which is 290. So this point is 290. 1.07. Good. You pick any 2 point on that straight line. Now we use the slope formula to find the slope of this line. Let's call this is x1, this is y1, this is x2, this is y2. Now we substitute. So our y2 is 1.18 minus y1 1.07 divided by x2 is 300.6 minus x1, that is 290, and this is, now I need your help, what is 1.18 minus 1.07? So that is it 0.11 divided by 300.6 minus 290? It should be 10.6. Okay, now what is 0.11 divided by 10.6? Can anyone help me? 0.11 divided by 10.6. .01. Okay, thank you. So we have 0.01. So this is the slope of a straight line. So our slope is positive. It means our line is increasing. Okay. Now, once we have a slope, we use a point slope form. So our point slope form is y minus y1 equals to m times x minus x1. So we have y minus our y1, that is 1.18 equals to slope 0.01 times x minus x1, which is 300.6. So this is y minus 1.18 equals to, okay, 0.01x minus, now 300.6 times 0.01. What is that equals to? 3.006. Thank you. So this is 3.006. Now we add 1.18 on both sides. Our y is equals to 0.01x. Okay, now negative 3.006 plus 1.18. So we get negative. Can you subtract that number from 1.18? That's negative 1.826. Thank you. 1.826. Okay, so this is our linear function, or we can rewrite this as a f of x. Our y is the same as f of x. Okay, do not get confused. So function f of x equals to 0.01x minus 1.826. So this is the linear function. Okay, this is the linear model for our given data set. Okay, once you plot, we get a scatter plot. Okay, and we try to draw a straight line, okay, on that scatter plot in a such a way that we include as many as points on the straight line. Okay, so this is our linear equation for given straight line. Okay, any question up to here? Okay, now the next here, what we are asked to find. Let's see what we are asked to find here. Okay, first question, let x denote the weight. Okay, that's what we did. Make a scatter plot of the heart weight, h versus x. Oh, okay, they call heart weight as a h. Okay, what we call we call y. Okay, so it's still same thing. Okay, that is, so our graph is the first part. In B, state in words any general observation you can make about the data. Now, from this data, or even from the graph, what can we say about the heart of a rat? So from this scatter plot, what kind of observation we can make? So our horizontal axis is the body weight of a rat, right? The vertical axis is the heart rate. Now, as the body weight of a rat increases, what happens to the heart weight of those rats?
It will also increase.
it also increases, right? So that's the observation we can make from the table as well as from the graph. And even though our slope is positive means our heart weight increases as the body weight increases. Okay, so that's the observation we can make. In part C, find an expression for the linear function that best fits the given data points. Okay, so this is the linear function that describe our data set. So this is part C. Now in part D, compare the actual heart weights for a given body weights with the heart weights predicted by your function. Now, so we have this function. Okay. Now for each body weight, we can make a prediction of a heart weight using this function. Okay. Now let's go back to our data set. So here, our function is, we have a function f of x equals to 0.01x minus 1.826. So this is a function. Now let's find a heart weight for each body weight using this function. Now how do we do that? So we have this function, okay, that describe this data set. Okay, so these are the actual heart weight. Now we will use this function, okay, to make a prediction of a heart weight for each of these rat. Okay, so these are our x values. We replace our x by this body weight and find out the heart weight. Okay, so when we have a rat with a body weight x equals to 281.58, so what will be our output, which is y, or which is f of x? So you replace x of this function by 281.58. So we have 0.01 times 281.58 minus 1.826. Now I need your help here. Can you simplify this? So multiply 281.58 by 0.01 and subtract 1.826. Zero point nine nine. Okay. Now in the similar way, let's take another body weight. Okay. So x equals to. Now I want you to use the calculator and replace your x by 285.03, and what will be the value of y? It's going to be 0.01 times this number minus 1.826. 1.02. Now let's do for the next body weight, which is 290.03. So what will be our heart weight for the rat with a body weight 290.03? You just replace your x by 290.03. Use calculator. Okay. 1.07. Let's take x equals to 295.16. And what is our y? .13. Let's do two more. We have x equals to 300.63. What will be our y? .18. And finally, when our x is 313.46, what will be our y? 313.46. 1.31. Okay. Now, so here we have the new heart weight for this rat. Now, what is the difference between this data and this data? So, what is the difference here? So, we already have the heart rate for these rats. Okay. Now, using our function, we calculated the heart rate. Now, what is the difference between this heart rate and these heart rates? So the heart rate given in a table, these are the actual heart rate of the rat, okay? But the heart rate that we calculated using this function is the predicted, okay? So we make a prediction of a heart rate of the rat using this function. Now, from this function, can we find the heart rate of a rat whose body weight is 500 gram? How do we find? So we have a function. This function gives us the heart weight for a rat. Okay. Now let's make a prediction of a heart weight of a rat whose body weight is 500 gram. Now how do we do that? You replace x of a function by 500 and you just do a calculation. We'll get the heart rate. Can anyone help me here? So just replace x by 500. Okay, so 500 times 0.01 minus 1.26. What will be that equals to? So let's make a prediction of a heart weight of a rat whose body weight is 500. Okay, so if we have a rat of a weight 500 gram, its heart rate f of x or y is equals to 0.01 times 500 minus 1.826. And this is 5 minus 1.826 and this is equals to 3.5 minus 1.826. What is this equals to? 5 minus 1.826. Can I know? Yes. 3.174. Okay, thank you. So 3.174 gram is the heart weight for a rat whose body weight is 500 gram. Now, if this using this function, now we can make a prediction of heart weight of any rat, right? So if the rat is like 1,000 gram, we can still make a prediction. Okay, our prediction may not be 100% accurate, but we can make a prediction using our linear model. Okay, so this is how we can use our linear function to make a prediction. Okay, any question up to here? So what we did, we were given a data set, right? We identify input, we identify our output. Input and output together, it's a point. We plot those points on our Cartesian coordinate system. We call it a scatter plot. Okay, now in the scatter plot, we make an observation whether we get a straight line or sometimes we might get a parabola. Okay, so in our case, our scatter plot give us a it's not exactly in a straight line, but it looks the data set are in a straight line. Okay, so we draw a straight line in a such a way that the distance of each point from a straight line is very minimum. Okay, once we have a straight line, we take any 2 points on the line, we find the slope, we use a point slope form, and once we simplify, once we solve for y, we get our linear function, and we using this linear function we can make a prediction. Okay, any question? So basically we are finding an equation of a straight line here. Okay, to find an equation we need to find a slope and we need to use a point slope form. Okay, that's what we do here. Okay, now let's go to the next one. Okay, so here now we have a new model here. So if we have a model that gives rise to a linear function of this form. So if our linear function f of x is of k times x, okay, or y is k times x, our k is greater than 0, then we called this model, okay, we call this function involves our direct variation. Okay, so we have a function, and if our function is k is any number greater than 0. Okay, for example, let's say we have a function f of x equals to 4x. So we have a number times x, and if this is the case, we call it the model. We call the model has a direct variation. Okay, it means our y output, okay, varies directly as x. What does it mean? It means as the value of x increases, our value of y also increases. Okay, as the value of x decreases, our value of y also decreases. Okay, so this is the direct variation between x and y. Okay, so when our input increases, if our output also increases, or when our input decreases, if our output also decreases, we call this a direct variation. And this is the equation, this is the form, okay, this is the function that represent direct variation. Okay, and here our k, we call k as a variation constant or a constant of proportionality. Okay, so our k is any number greater than 0. Okay, that is a variation constant or a constant of proportionality. Now we have an example here. The volume of a fixed mass of a gas is directly proportional to its temperature. Okay, so we have a volume. Okay, we have a volume, and volume is directly proportional to its temperature. Okay, directly proportional to its temperature. Directly proportional means as the temperature increases, volume also increases. As the temperature decreases, volume also decreases. That is the directly proportional. Okay, if the volume of a gas is 450 cubic centimeter at 300 Kelvin, find the following. So we are asked to find the variation constant. Okay, now every time if you have a directly proportional, then you have to use this expression y equals to kx. Okay, so you have to use y equals to kx for directly proportional. Okay, in our case y output is the v, so we have v equals to k is a constant and our x is temperature. Okay, our v is the dependent variable, volume depend on temperature, temperature is constant. Now let's so we know our volume is 450 cc, so let's replace our v by 450 equals to k. This is what we need to find. Our temperature is 300 Kelvin. So let's solve this equation for 300. For that we divide both sides by 300. 450 divided by 300. Okay, this is, what is this? 450 divided by 300. Is it 1.5? Okay, so 1.5 equals to k. So our variation constant k is 1.5. Okay, now in part B we are asked to find the volume of a gas at 340 Kelvin. So we are asked to find v, so v is unknown and this is our temperature. So we use this formula, v equals to kt. Okay, k we already know what is k, 1.5, and our t temperature is 340. And 340 times 1.5, that is 400. What is 340 times 1.5? 510. Okay, 510 cubic centimeter is the volume of gas when its temperature is 340 Kelvin. Okay, so this is how we can use this. This is also a linear model. Okay, and this linear model, it involves direct variation. And if you see this directly proportional, your function always looks like y equals to kx or f of x equals to kx. It's the same thing. Okay, any question? So look for the keyword. Okay, directly proportional. If it's directly proportional, your general formula is always y equals to kx or f of x equals to kx. Now the next we have a inverse variation. Okay, so in inverse variation, our function, so if our function is k equals to x, okay, we have a function f of x, and if our function is equals to k divided by our input x, or y equals to k over x, then this linear model so this model, this is not a linear, but this model involves inverse variation. So inverse variation means if our input x increases, then y decreases. If our x decreases, y increases. This is an inverse variation. Okay, so in direct variation, if x increases, y also increases. If x decreases, y also decreases. But in the inverse variation, it's opposite. Okay, if our x increases, y decreases. If our x decreases, y increases. Okay, and this is how we rewrite our inverse variation. Okay, and here k is a variation constant or constant of proportionality. Now here we have an example. The price of a product is inversely proportional. You see a keyword here, so inversely proportional. So we have a price of a product, let's call this P, and this P is inversely proportional to its demand. Okay, we have a demand, they use P for the price and okay, Q for the number of products demanded. Now, since it's a inversely proportional, our equation is always P. Okay, our equation is P equals to K divided by our Q. Okay, so using this function, we have this formula. Now, if 3000 units are demanded, so what is this 3000 units? This is Q, demanded at $10 per unit. So this is P. How many units are demanded? So how many units means how many Q are demanded at $6 per unit. Okay, so at first we need to find the K. So our Q is 300, so let's replace our P by 10. So our P is 10, K, this is unknown, Q is 3000. Okay, now let's solve this for K. For that we multiply both sides by 3000, so this is gone. Our K is 30,000, right? So this is the variation constant. In second case, we have to find how many units are demanded at $6 per unit. So how many units means we need to find Q. Okay, we use the same formula here. So P equals to K by Q. So we need to find Q. Our P is 6. So our P is 6. K, we know what is K, that is 30,000, and our Q, this is what we need to find. Now, how do we solve this? So let's get rid of denominator by multiplying both sides by cube. So this is cube cancel. Okay, this is cube, not 9. So we have 6 cube equals to 30,000. We divide both sides by 6, and our cube is equals to 5,000 unit. Okay, so this is how we can use inverse variation model. So look for the keyword. Okay, so if you have a directly proportional, then you have to rewrite your function as a y equals to kx. Okay, k is a constant that you need to find. Okay, if your variables have a inversely proportion, then our y is k divided by x. So look for these two keywords. Okay, if it's direct, y equals to kx. If it's inverse, y equals to k over x. Okay, any question up to here? I'm sorry. Okay.